Believe me, believe me, this video is gonna blow up your mind. When you talk about computers, the first thing which really comes to our mind is the speed, incredible speed. But usually when we do study cosmological data analysis, the speed gets reduced because of the heavily computing involved. When we are doing MCMC, a lot of models involved. If we are even taking the simplest data sets, let's say Hubble data sets, and with the lambda CDM model, again, we are not going to get a lot of fasting. We are doing MCMC, but our computer is not fast. But today in this video, I'm going to share you something incredible that I have written the code which increase the speed up to 10 times than your usual speed. When I'm talking about the 10 times, even with the we are not talking about any supercomputer. Even with your laptop, you can achieve this 10 times speed. So if you want to understand if you want to understand the whole thing in this particular video, then see till the end. I'm going to share you everything how I have achieved this 10 times fast, and I'm going to share this code, and you can find it in my GitHub channel. So let's get started. So first of all, what we are going to do is that we are going to first understand how we can write our code. In the previous video, I have already shared how to construct your model, what is the meaning of data analysis, and how you can write your code. But today I'm going to also recap this in a lightning speed, and then I'm going to show you that, okay, how I have written the code so that it is producing me 100 times faster than your usual computing speed. So here is the basic structure of the code. First of all, I'm going to import some libraries which is written in the Python, where I'm importing NumPy, some Matplotlib, some Corner, and SciencePy using integrated and so on. So over here for this lambda CDM model, you do not require all these things, but again, this is for the wide range of models. You can just copy and paste it. Second thing, that we have the Hubble data. In the Hubble data, you have the redshift data, the column for the Hubble data, and the column for the error data. So this column, that Z data, S data, and S error, we have extracted from the data which is loading from our computer, and then using the NumPy, I am first H error to diagonalize it, and then I am going to calculate the inverse. It is just show you that, if you don't have any diagonal matrix, how you can make a diagonal matrix, and for the diagonal matrix, how you can even calculate the inverse. It is not only true for the diagonal matrix, but you can calculate the inverse of any particular type of matrix. And now in the future video, in the upcoming video, I'm going to show you the analysis using the supernovae data, which I'm going to take Planck 1701 data sets, in which we have the covariance matrix. This covariance matrix is basically telling you the correlation between the measured value and the telescopes and all these things. So for that, you have to inverse it. Therefore, I am using the same technique to inverse my S error data sets. In second thing, first of all, I have defined my model. This is the simple lambda CDM model where you have OM0, and then for the constant equation of a state -1, we have the dark energy 1 minus omega m0, and this returns my H value. And then I'm calculating the chi-square using my NumPy array and my matrix technique. And then I am using the model parameter, that okay, I have some kind of parameters in my model and I want to constrain it, and therefore I am trying to see that what is the theoretical value for this type of model parameters that will be generated by my MCMC. And then I'm using the Hubble chi to calculate the chi-square between S theta, ST, and Hubble error. And then I'm going to define my log-like parameters, because when you calculate a chi-square, then what you are usually interested in the log value of that chi-square, which is defined as -0.5 times some model parameters. Now comes to the MCMC part. For the MCMC part, we are going to have to iterate, and then it generates some kind of walker. So for some particular iteration, it will generate some kind of 30 walkers which will roam around some kind of grid, and will try to find that it will try to find the chi-square and try to minimize it. And this is how we are generating n walkers. N dimension is 2 because number of the parameters, and iteration I'm taking 10,000. It's use, but obviously to have very contour plots, you require this 10,000. And then I'm going to randomly generate my model parameters using the random uniform. So I'm constraining this between low to high. So this is low is 0.001, which is for the matter density, and high it can go up to 0.6. Again, simply for the h0, I'm constraining h0, it can take low value up to 30 and the high is 90. Then I'm defining size and walker depend and n dimension. So size is kind of matrix. And then I'm counting n CPU, and for the pool I'm taking, because of I'm using the parallelization, because I have to make it faster. And first of all, I will show you that what happens if you just having the one process, and if you are increasing, because in my CPU I have like 6 cores, and 6 cores having 12 CPU, I cannot use my 12 CPU, but I can at max use 7 to 8. So it is feasible. And then once your MCMC is done running, then I'm going to get my samples, and these samples have a chain, and this is important to plot the distribution. And here I'm going to plot it. First of all, I'm going to take some kind of percentile, that what is the 16 percentile is 1594, and from there I'm going to take the median values of OM and H0, and then I'm going to write it in the file with it, which is math info.txt. And also I will extract, I will not only extract this omega m0 and h0, I will also write I will calculate AIC and BIC. It has the testing that how good your model is, and for the comparison of different models with respect to the lambda CDM model, you can always calculate these AIC and BIC. All right, and now using the getDist, I have this code, and I'm going to plot the triangular plots, which shows you the correlation between these parameters. And here after that I got this omega m to be 0.86. Yeah, sorry. So this is my triangular plot. So you can see this very fine structure, fine contour plots, which you have already seen in many papers, h0 and omega m0, which is in the this is the deeper red shows the 68% of confidence, and the outer range is 95% of confidence. And in the title which you are seeing over here, this is for the 68% of confidence. So I have got H0 to be 70.6 plus minus 1.5. On the other hand, I have omega m 0.258, about 0.26% of dark energy we are in. So if you have 26% of dark matter, then rest of the thing is dark energy. All right. And here is the values that I have got omega m as 0, and these AIC values and the BIC values. So I have run it for the 50,000, and my n walker is 30. Now come to the interesting part, the code. So when we are talking about the code, I have first of all the basic code, which I have already shown you right now. So this is the basic structure of the code, and I am running using my WSL because I am using Windows. Yeah, very good. So I'm using Python 3 lambda cdm.py. So as you can see over here, that for the 10,000, and if I'm using the 30 walkers using just one processor, I have an incredible speed of like 100 to 120 iterations per second. If I am just using my 7 processors, let us say I have the 7 processors, what would be the speed? Before that, I have to interrupt it. Again, I'm using this one. The speed has increased up to 140 and 150 iterations per second. It's not bad at all. I have to admit it. It's not bad at all, and it's incredible. It's not bad at all. But for an example, if I am using just one processor, and if my n walkers is approximately 100, then what would happen? Again, I'm stopping it. I should not. And then you will see that your speed has now dropped to 40 to 50 iterations per second. All right. Now, as one can say that we have only 2-dimensional parameters, then using too many n walkers is not going to be give you a good result or great result. So I can say that okay, very good. But this video is for showing you the purpose. This video is for the purpose of giving you the idea that how the speed we can get. So for this one we have a great speed, but right now I'm going to show you something incredible. So you can see the speed over here, 50, 51, and if I have 30 walkers, then you can see the speed. All right, let's do another case, and let's choose I'm not going to use the parallelization. First of all, in this code I'm going to use 10,000 and with the 30 n walkers. All right, you go over here, and then I'm using typing python 3, and I have Cython executive dot hubble dot py. Right, come on. Oh my god, this is 1400 iteration per seconds. My god, it's like 130 times 10, so it is 10 times greater speed. Super man, it's lightning speed. Even if in a MCMC without using any parallelization, I can achieve 10 times faster than my simple coding. Oh my god, what happened? Let me try with another thing. Let us try with 50,000. How many times it will take? Usually it takes a lot of time, but let's run it. 1300, even if less than 30 seconds. We don't have to don't have to wait for long. Means that for 10,000 it took only 7 seconds. For the 20,000 or 50,000 it will just take only 30 seconds. You can see the incredible speed. And I'm going to also show you the plots that we are going to get in this case and everything. So you can see, guys, this is the speed. When we are talking about the computers, what we are very interested to see the speed, that you are doing a large number of iterations and you are getting the error, getting the result within a finite time. So this is for the Hubble data. You already know that Hubble does not have too much data, so it has some speed. But when you have some complex type of model, then the speed has reduced. But if you use usual type of coding, then the iteration would be like it will take 20 to 30 seconds for one iterations. But with my optimization, I have optimized my code in such a way that the speed I am gaining is incredible. I will tell you that how I have optimized it, but I am going to show you that okay, fine, what are my chains? Hubble OHD chains. So where is Hubble OHD chains? For Hubble OHD chains over here. So you can see these Hubble OHD chains. Amazing. 70.6, 0.258. Similarly, I can find corner plots using the corner. So corner plot OSD, where is corner plot OSD? This is the corner plot. You can see that incredible plots that I have got over here. Also, I have the statistics that I can show you AIC, BIC in Hubble statistics. So Hubble statistics info over here, and you can see this incredible thing, 29.76, and BIC is 33.28, 70.60. So you see that if I'm using, let me just show you that if I'm using 30, if I'm using the 30 n walkers, I have incredible speed. Let's just increase to 100, and I will also show you that okay, fine, as I have told you that this won't again you have to wait for just only 1 minute 20 seconds. All right, now as you are increasing the n walkers, because and you are increasing the dimensionality at which it will search. So the dimension has increases, the grid point has increased. That's why it has now reduced to 500 to 600. All right, but you can see the incredible speed over here. So this speed is approximately 600 and with 50,000 iterations. So that is the beauty of this optimization, which I personally like too much. and I will show you in a minute that how I have found this kind of optimization. So for just I'm going to give you some brief idea about what happens in Python. So when you Python is a higher level language. For an example, you can just print a plus b, and you just invoke a to be 2 3, it will print you 5. A is 2.2 3.3, it will give you that 5.5 without even specifying which data you are going to give. So when you are doing nothing, when you are just giving some kind of variable and you are assigning to value of it, and it will give you input inside the Python, there are a lot of layerings. It will compile those layerings, and then it will give you the output. So that is one of the reason that we have the CPU. So CPU understand everything in ones and zeros, and then there comes some kind of interpreter, that how we are writing everything in English, and then there is an interpreter, and this interpreter is giving you everything. But again, the interpreter requires that what kind of data values you require, because they understand only in the binaries. So who is conversing your a is equal to 2 and b is equal to 3? Who is telling you that we are using integers, or we are using the fractional values? All right. So for an example, if you have anything, if you ever have code in C, then you have to write several steps. For an example, you are writing some header file, and then you are assigning that this value is up to integer or the float or the double value, right? And then it will give you. So C or C++ is called lower level language, where it has just only one layering. So you are writing everything, you are telling you're telling the interpreter that what kind of a variable I am assigning, it's int or something else, and then it will simply use the CPU and so on. On the other hand, when you are working with the Python, there are a lot of layerings. There are a lot of several codes have been written in the libraries. It will fetch it out, and then it will show you. So if you add 2 plus 3, it's a lightning speed. But if you just use some kind of computing expensive codes, then it is taking a lot of things. So what if I can use C and also my Python? Because if I write the C code, it will have just only one layering, and the incredible speed that you have already seen. So what I have done is that I have written some piece of my code in C and some of the piece of my code in Python. But the problem is that Python and C is completely different regime. They are completely different language. Then you have to integrate it. And when you want to integrate it, then there comes us called Cython. It is a superscript language which, having some interface between C and the Python. So the thing is that it is kind of superscript language which supports C language also and supports Python also. All right. So what I have done is that because I am good at Python, so what I am writing is that I am writing everything in terms of Python, but I am using the C extension over there. All right. So I am first assigning that what kind of values I am taking and on the and all these things. In the Python, I must add that in Python you have the infinite amount of precision, but in the C or C++, you are assigning that it must be double or something. So they have the limited range. If you have heard about double, long int. So it depends on the architect of your processor, if you have 64-bit or 32-bit. So that is one of the limitations. So if you are working with the several order of magnitude, then it's going to be a problematic. You have to be very careful related to those things, that what kind of order of magnitude we are working of it. Right now, since we are working with like 3 to 4 precision of decimal points, then we don't have to worry about too much thing. We can just write it down. So the idea is simple, that you have to figure out in your code that what kind of code, what are the portion of code is basically taking your lot of amount of time. What you can do is that you can shift those codes to C language, and then you just call those things to your Python, and then you can run your MCMC. And you have to understand that your Emcee basically written in terms of C and other libraries, and also in the Python. So it is highly optimized. You don't require Cython to optimize further your Emcee. But in your pieces, as I've told you over here, that I have over here several things. For an example, lambda cdm pi. So first of all, I am invoking the model. So it will take z values and parameter values, and then it will return me h value, right? So it will compute np of square root. So again, if I'm using the Python, it will take a lot of time, but if I'm using the C, it will give me instantaneously. Over here, this data point is fine because again, I'm using the NP library. NP NumPy library is also written in C, C++, and all these things, and it is again highly optimized that you don't have to do anything. Similarly, I'm calculating chi-square using my dot product matrix multiplication. So again, it is also optimized. On the other hand, I have the model parameters. I can also use this in my C language. Similarly, this h log like, I can also use, take the advantage of direct C, that okay, fine, I will give you all the assignment and then so on. So what I have done is that this is called Cython execution hub. So here I am just writing the pieces of code which I need to write in my Python. So I am just taking these data points and then these likelihoods, that okay, fine, these likelihoods come over here. And because these likelihoods, I am running the MCMC, because you have to give the input of MCMC, and MCMC has told you that it is better to write MCMC or EMCE in your Python. It's great. And over here I have made a Cython file, that Cython lcdm.pyx. So you have to give the extension. If you are using Linux, you have to give the extension of pyx. If you are using Windows, you have to give pyd. So over here I am importing C import Cython, import OS, import NumPy. You have to understand that Cython is a super script, so it is also supporting all the libraries that already built in the Python. It also support a lot of libraries of the C. So that's why it is kind of super script language. Again, I am taking the data points using the NumPy, and I have defined over here that what is my model parameters. So but the definition is quite different because I'm using Cython. It is not a Python. So I'm first defining CP definition. So it has some C and P. So it is working as a wrapper, that it will give you the C extension as well as the working as a Python, and you have to say that okay, what kind of data type it is returning, and then I am just usually defining my model parameters. And now you can see that my Z is the redshift. So I have to ensure that what kind of data type I am using, it is doubled. Similarly, I'm using parameters. So parameters is array. In terms of in Python, you don't have to write anything, any array. If you just using the list, it will automatically give you list. But in C language, you have to give the array particularly, because in C you have the pointer and it will go at each address and you try to extract those values. It is incredibly fast. So I am using that. Okay, for in the parameters I have an array. In the array I have these floating values. So over here I am using parameters of 0, parameters of 1, and parameters of 0 corresponding to om0, h0. So I have written everything like this. And then similarly I am calculating the chi-square using the for loop, because you can understand that if you have ever coded in the C, the for loop, you have to mind it. In Python, the for loop, whenever you are using loop, maybe while loop you are using or for loop, it is incredibly slow, mind it. So you must avoid any kind of loop inside Python. So whenever you have this kind of loop, you write it in Cython. All right, so I've written everything in Cython, and again I am using these conditions that okay, fine, I am taking the model parameter over here and it returns me the Hubble chi, right? And then again I have this log like. I am using 2 times, I guess, but yeah, it's fine over here. There is no problem to it. So over here I am calculating STI, and then I am calculating the this log. So by the way, I'm not using this one. I am just using the model parameters, and then once this is done, you have to make a setup file. So this is the way of you have to make a setup file. So first of all, you have to install setup tools and take import setup. Again, you have to use the setup tools and take extensions cython.build, cythonize, and import numpy, because this is the very basic level code. But in the later on video, I will show you that how to work with the supernova data, Python plus datas. and then you have to write the setup code, extension module, Cythonize, whatever you have written as .pyx, you can just write over here. And if you are using the kind of cp dot some array kind of file, then you have to include this kind of directories. All right, so once it is done, what you have to do is that you have to take this one and you have to use python 3 slash setup. Yeah, so this is the code that you have to write. Python 3 setup.py build external in place, means that at the same folder. So once you will hit this button, then you will see that there are a lot of several codes. Let me just show you. So Cython.pyx, again, let me just see that. Okay, h log like Cython, h log like Cython. So it is basically, let me just change you by this one. All right, so it will notice some change, and again I'm building it. Yeah, so this is how it will build it. So you have to write your code in Cython in such a way that it is producing this one. If it is giving you error, then you have to fix the error. So you have to be intelligent. So what it basically does is that it will produce the C coding, the optimized C coding of your Python code. So what my Python was cython.lambda.c. So this is my C version of this code. You can see that this is the C code of this one. It is like about 28,000, 29,000 lines of this code. So my simple Python has generated the C coding, and I'm using the Linux WSL. So here it will also produce .so file. All right, so once my setup is complete, I have to run it, and then once I have run it, then what you have to do is that you have to import, not this setup, we have to make an execution file, and you have to import cython.lambda.cdl. So from here you have made a several definition block. What you can do is that if you want to call it any of the block, you can just say that Cython lambda cdl, in my case over here, dot that block, h log like Cython is the block which is basically calculating the chi-square. I am using this one. Understood. I'm using the values that, okay, fine, whatever the value, it will simply calculate the chi-square and it will return it. So over here it is calculating the theoretical value. This is Hubble chi-square, and then it is calculating the log of this one. I am calling that one Cython lcdm as log like. I am defining over AIC BIC because these are very simple things. Understood. And then I am running this MCMC, and when I am hitting the button, you can see the speed. So I have to, again, you can use this Python 3 Cython just the way you are running any Python file. You have to just use the same code to execute it, and then hurrah. I'm not using any parallelization. As you can see over here that in my MCMC, I'm not using any parallelization. But one can say that, okay, you can use parallelization. The thing is that if you were using, the speed gets reduced because you have everything written in the C, and the pool or any other way you will write, it is not going to work in that way. So it becomes hurdle. So you are using C libraries, you are using the C interpreter, and you are trying to call it using your Python. So if you are using the multi-processing parallelization, it will not going to work. You have to use different kind of parallelization, which is again a lot of optimization you require. But for this kind of thing, it is perfect. So I hope you will enjoy this video and you enjoy seeing the speed that we have achieved it. All right, and you understood that why Python is not good for doing this kind of thing, but you can use some higher level optimization in my later on videos, where I will show you that if you have a complicated model, it is not, you are not going to able to find the solution, analytical solution. You have to rely on the differential equations. All right, family of differential equations. So consider you have family of differential equations. How will you solve it and how will you fit with your model? Understood. And I will also show you that if you will use just simple ordinary Python coding, you have to wait for 6 days, 7 days, many days. But I have spent a lot of, like, approximately 100 of hours to optimize this code. All right, and this code will produce you instant results, even if with the Pantheon samples, where you have to calculate the 1701 by 1701. All right, the speed is incredible. It will show you that 5 iterations per second, so it is huge speed than waiting for one iteration, 20 seconds for one iteration. All right, so I hope you like this video, and if you want to find this code, I have already made my github link. I have given in the description box. You can go and check it out, and please let me know how you have liked this video, or if you have ever heard of this kind of optimization before. All right, so this is not just only one kind of optimization, we have multiple optimizations. All right, so I will talk about in my later videos how we can achieve those things. People won't share you too much, or you can find this kind of optimization thing maybe in some kind of Monty Python. They have simple MC. These are people have already done a very complicated files using the C as well as Python, and all these things are involved there. But I am giving you that, okay, how you can as a scientist in your laptop write your own code and optimize it. All right, so if you like this video, please sharing is the most important part, because you know why I'm making a video. The motivation of making my video is that one who is starting their research career, or if you are new to data analysis, you don't know anything, just like I didn't know anything about it, so you will not find many people to work you out. All right, so that is my video will must do that. Okay, it must give you the direction to get into those kind of state of the art research. So I hope you like the video. Please hit the like button, subscribe button, and share to your friends. This is the Minato Cap signing